Okay, so welcome everyone to lecture 23. This is, we'll have this week and next week, I think, will be the last week of the course. In this lecture, I wanted to describe the topic of interior reconstruction in AdS CFT. You'll probably remember that last week, we discussed a number of paradoxes that had to do with large black holes in AdS CFT. So the paradoxes that we were discussing, did not apply to black holes in flat space, but they did apply if one considers large black holes in AdS. The essence of these paradoxes was that, maybe typical states in AdS CFT contain firewalls, or at least that the boundary theory does not describe the interior of typical states. And it's important that everything we were referring to was about typical states. So later, I think probably in tomorrow's lecture, we will discuss a resolution of these paradoxes. So these were paradoxes about typical states. And we will discuss a resolution to these paradoxes that emerges from something that we'll discuss, which is called state dependence. And then we'll discuss the consistency of state-dependent constructions, and to what extent state dependence is consistent and viable, and so on, and why we might expect it and where else we see it. So we'll have some discussion about that. But for today's lecture, I want to ask a simpler question, and the simpler question is just as follows. Let's say we there are these paradoxes about typical states, but we all agree that there are some states in AdS CFT, or some large black holes in AdS, which do behave like the typical classical solution does, in the sense that they have a smooth horizon and an empty interior. So leaving aside the question of how these paradoxes are resolved, which we will discuss tomorrow, today I just want to discuss a simpler question, which is, say psi is a state with an empty interior. I will use the terms empty interior and smooth horizon synonymously. Because when we say empty interior, I just mean that the interior, there's nothing near the horizon. There might be, there's of course stuff deep inside the horizon, and there's a singularity and so on. But when we say empty interior, it really means, something where if you go just inside the horizon, you don't see anything. And I'm going to use that synonymously with the notion of with the phrase smooth horizon. So sometimes I might interchange the phrases, and please don't get confused. So the question we want to ask today is, let's say that psi is some state with an empty interior. And we agree that such states exist, right? So whether or not psi is a typical state, we will postpone for now. And we will, let's just consider some such state. And then the question is, how do we describe its interior? Okay. So let me just try and make this question a little bit more precise, right? In AdS CFT, we have some set of we have a Hilbert space, and we have some set of operators that live in the boundary theory. There are also some set of operators that live in the bulk theory. So in particular, imagine that we have some scalar field, which is the example that we've been considering throughout this course, which is a bulk operator. So if we believe the dictionary, then we believe that there should be some boundary operator that describes this bulk operator that is equal to this bulk operator. And when we ask the question that we are asking here about how do we describe the interior of the state, what we are asking is, let's say we consider this operator where this R is inside, so it is smaller than the horizon radius. So the question is, what is in the CFT? So when we say, how do we describe the interior, the question we are asking, and that is in some sense the precise question that one should always ask when you want to ask how do you describe a certain region in AdS CFT, The question is, what are the CFT operators that probe the interior of the black hole? Okay, so that's the question that we want to ask today. And we are going to assume, as I said, just for today's lecture, that psi is a state which has an empty interior. So it's not one of these firewall states. And you'll see in a minute why that assumption is important. Okay, so before we go on to this discussion of how you describe the interior of these black holes, it's useful to just remind ourselves of how one describes the exterior, right? Because corresponding to this question that we have written in front of us, there is a similar question that one can ask, which is, how do we describe the exterior of the state psi? So let me just remind you how we describe the exterior of the state psi. So of course, dual to this phi, this field phi, there is an operator that lives on the boundary, which is this operator. Right? And we can Fourier transform this boundary operator. So because we have, so there's no r coordinate, but there is a t and there's an omega. This runs over the st minus 1. And remember, as we said last time, we are always considering black holes in global AdS. So we can Fourier transform this O of t omega to get some Fourier modes, where this is the frequency. And this is some generalized angular momentum quantum number. So because we might have a sphere in higher dimensions, there might be many quantum numbers that are associated with this. But all I did was I took this operator O of t omega and I integrated it with e to the minus I omega t and some spherical harmonic. And then I have this Fourier transform, which are the modes of this operator O. Then the answer for what happens in the interior of the black, or what happens in the exterior of the black hole, is quite simple. And the answer is just that in the exterior, we write down this field just as a sum of all of these modes. These same modes, these are the modes of the boundary operator. So these same modes, we write down these same modes, we write down the e to the minus I omega t, we write down the spherical harmonic, and then you need to write down a radial function. And you write down a radial function, which is some function of r. And this radial function is fixed by demanding to leading order that this field satisfies box minus m squared phi is equal to 0. Of course, you could ask what happens if the field in the bulk was interacting, and then you would have to correct this prescription that we had. But just the same way that you can start with some Fock space description in the bulk and then correct that perturbatively, we believe that you should be able to start with this description that we have here, which is the description in the free field limit or the n goes to infinity limit, and then correct that perturbatively. So for the purposes of the, to the approximation in which we are working today, this is already a sufficient description of what's happening. Of course, so this, as I said, fixes f. Okay. And there's a boundary condition on f, which is the boundary condition that we have above, which is that this goes to 1 by r to the delta times some coefficient, which might depend on omega and L, and that coefficient, well, maybe if I normalized it, actually, if I wrote a omega here, this coefficient should probably just be 1. Okay. So there's this boundary condition in f of omega, and then there's an equation that f of omega must satisfy. Of course, we can renormalize these omega modes. So instead of writing in terms of these omega modes, we can write down some creation and annihilation operators, which are simply this divided by some term, so that they have the property that they're canonically normalized. Okay, but whether we use A or whether we use O is just a question of some C number, some C numbers. If we use A, then we might get these constants that I described previously. If we used O, then we just get some factor of 1. But the point is that the answer in the exterior of the black hole is just a simple answer. You just take the boundary value of the field and you just extend it into the bulk using the bulk equations of motion. Okay? Let me emphasize here that, we are not trying to describe, as we've discussed many times in this course, the essence of AdS CFT is the fact that the boundary theory at one point of time knows about what's happening in the bulk. But the construction that we have written here is much less ambitious. It's actually using the boundary theory at all points of time and using that to reconstruct what's happening in the bulk. And the reason it's using the boundary theory at all points of time is because you see here you have the Fourier modes of O of omega, which are obtained by taking the field O of t omega and doing an integral over all time. So what you're doing here is really that, you know, you have some boundary, this is the horizon, you have some boundary conditions here, which are O of t, and you're using that to solve for phi of t in this region. Okay? So you can use the boundary conditions and an equation of motion to solve for phi of t in the region outside the horizon. And that's what this exterior reconstruction does. Okay. Okay. So far, so good. Let me just make one comment. There is some subtlety about how how this construction should be written in position space. So notice that I've written this construction in momentum space because I've used the modes of O, and even though the field on the left-hand side has some position argument, what appears on the right-hand side are some modes of O, and it's in fact non-trivial to try and Fourier transform this and write this as an integral over O of t omega. And there's some subtleties that are associated with that, but that don't concern us. Apart from those subtleties, there's no particular issue in using this construction. Of course, this is a construction that assumes spherical symmetry in the bulk. In general, you might have some geometry that's more complicated. But for our purposes, since we're interested in some conceptual issues, I'm actually going to drop the L index, and I will write operators that look like A omega or A omega dagger, maybe O omega. Okay? The L index is not going to play any particular role in what we're going to do. Okay. Okay. So this is the construction of the field outside the horizon. And the question we want to ask is, we know that if you take the field and you extend it inside the horizon, and inside the horizon, dual to these modes A omega L that we have outside the horizon, we also need some mirror modes which we'll call A tilde omega. These are the modes that we have studied at great length previously. They're the modes that are obtained by taking the field and by doing an integral. So they're the modes that are obtained by taking the field and doing an integral. So if you do an integral in this way, then you can pick up these A omega tilde modes. You have the A omega modes outside. Because we are in AdS, the A omega modes also have a left moving component, and that left moving component just carries through. But as we've discussed, in this course several times, there has to be some right moving component inside the horizon, and that right moving component has to be, has to have some degrees of freedom, which we have in the past denoted by A tilde omega. And the question is, what are these A tilde omega operators that we need to describe the field inside the horizon? Okay. So of course, one guess might have been, why don't I take A tilde omega equal to O omega? Or equal to, I don't know, maybe let's take A tilde omega equal to O omega dagger. Okay. But you can check that neither of these guesses that we've written down obey the right conditions that we need for these operators A omega tilde. In particular, as we discussed also last time, we require some correlators for this A omega tilde, and the correlators are of this form. But we also require some commutator, in that we require these A omega tilde, A omega to be equal to 0, at least to good accuracy. And you can check that neither of these guesses that we have, I mean, you could multiply things with an e to the minus beta omega by 2, but this guess would not work because it would just not have the right correlation functions. It also doesn't have the right energy. This has the same energy as A omega, whereas A omega tilde has the opposite energy. This kind of a guess would not work because it does not commute correctly with A omega. So this kind of an operator has a wrong commutator. So if you thought that, we will make the annihilation operators inside, the creation operators outside, or do something clever like that, that won't work. Because it will lead to non-zero commutators, appreciable non-zero commutators at space-like separation, not the subtle gravitational effects we've been talking about, but just commutators between the field at spatial separation, and that is a problem. Okay, so the question we want to ask is, what are the operators A tilde omega, so that they satisfy the conditions for a smooth horizon. These are not the only conditions. We wrote down in the beginning of this course some other conditions, but these are two of the conditions that are important. Okay. So this is what I want to describe in the rest of the lecture today. And as I said, we are working about a state where we believe there is a smooth horizon. And because we believe there is a smooth horizon about this state, or, we are told ahead of time there is a smooth horizon, we believe that such operators should exist. It should be a problem that has a solution. Such operators should exist because we said that there is a smooth horizon. Okay? So before I define these mirror operators, we need to take a slight detour, and we need to define some other notions. One of them is called the little Hilbert space, which we will describe. And the other is the notion of an equilibrium state. And then we will proceed to understand what these operators are in the CFT. Okay. Are there any questions about where we are heading or what we would like to do? I have not described the technical aspects of the construction, but I hope it's clear, what it is that we want to do. And if there are any questions about that, I could take them now.
Yeah, I wanted to ask, is this setup any different from what we did towards the beginning when we were deriving Hawking radiation?
Yeah. So in the beginning, that's a good, in the beginning, we just said, look, we have a field phi, which is defined in the bulk. And we assume that the field phi is defined both outside and inside. And then we said, you integrate the field with some modes, like these kinds of modes on behind the horizon, some right movers behind the horizon, some right movers outside the horizon, and we get these operators, which we call A tilde omega. The question we are asking today is, in the CFT, there are some operators. There is a Hilbert space in the CFT, and there are some operators on the boundary. And we have argued, we have given also, of course, there's AdS CFT, and we've in this course also argued, how the boundary in any case should have information in any theory of gravity. But let's say we just restrict to some example where there's a well understood AdS CFT conjecture. So the question is, what are these operators A omega tilde, right? So in the bulk, if there is a smooth horizon, you're right, you should be able to take phi and you should be able to integrate it and extract these A tilde omega operators. But there should be some operator in the boundary theory that is the same operator. So the question is, what is this operator A tilde omega in the boundary theory? So that is the difference. In terms of the bulk effective field theory, these operators are things we've encountered before. But we want to say, here we believe we have some description of quantum gravity, and how do we find these operators? And this is important because this is what is relevant for the paradoxes that we discussed last week. The paradoxes could be phrased as a statement that these A tilde omega operators don't exist, and they don't exist in the CFT. So it might seem from the bulk effective field theory point of view that you can define, you can just take the field and integrate it and so on. But in reality, you're fooling yourself because, at least the paradox says that you're fooling yourself because there's some other general principle that comes from various other considerations that we discussed last time that tells you that these operators just don't exist, and so there's no interior. Okay? So the question we are trying to ask today is, at least in some cases, can we find what these operators are, and then we'll discuss what we need to do for typical states. Does that answer the question?
Yeah. I have one more nice question. Yeah. Isn't the entire algebra on the bulk just defined by these omegas?
Yeah. In some sense, the algebra on the bulk, you're right. So the omegas are the only fields that live on the boundary, right? So that means that the entire algebra in the bulk should be defined by the omegas. So you're right. So in some sense, the A tilde omegas should be writable as some complicated version of the omegas. But the question is what, right? So let's say it clearly can't be this. It can't be we just take A tilde omega and write it is omega, or it is omega dagger, or put some factors, because that doesn't have the right properties. So in some deep sense, the omega operators are like, a complete set, or the boundary operators are a complete set. But that doesn't help us in answering the question of what are these A tilde omega operators. Maybe they're omega to the power 100, or maybe they're some polynomial in omega or something, right? So the question is, well, what are they and how do we define them? You're right that in the end, they have to be expressed in some way in terms of the omegas.
Right. Okay. Okay. Thanks.
Okay. Okay. Great. Okay. Great. So
yeah. I have one more question about this.
Sure.
A follow-up of the earlier question. So the question is, there is the statement that all the bulk algebra is in a sense described by the O omega K omega L. Is it guaranteed by the fact that we have a smooth horizon assumption?
No. This is just guaranteed by the if you believe AdS CFT, because the boundary algebra is defined is complete. They're only the boundary operators. So I mean, it doesn't literally mean omega, but if you take all sorts of boundary operators, if you take omega and the stress tensor and all sorts of boundary operators, but you see in the end, if you take like maybe even the stress tensor and a few other boundary operators and you start multiplying them together in all possible ways, that will generate the whole algebra. So on the boundary, there is nothing else. So it's if you believe that the boundary description is a complete description of the bulk, then there is really nothing else. The omegas at least generate the entire algebra. Of course, you have arbitrary polynomials of omegas.
And does it also mean that the horizon should be smooth also? I mean,
no. This by itself doesn't mean that the horizon should be smooth or not. This is just a statement of what is the operator algebra in the theory. So this is just a statement about the operator algebra of the theory. The question of whether the horizon is smooth or not is a question that depends on what the state of the theory is. So it could be that the state of the theory is a one kind which has a smooth horizon. Another state might not have a smooth horizon. And the question we're asking is, do typical states have smooth horizons? And that's some question about what is the bulk. The fact that O omega is a complete algebra doesn't tell you whether typical states have smooth horizons or not. Maybe typical states are fuzzballs or firewalls or something else. And the fact that O omega is a complete description doesn't rule out the fact that typical states are fuzzballs or firewalls. So we need to ask a more detailed question. So the statement that O omega is a complete set is kind of if you believe that the duality holds, then omega must be a complete set, or at least must generate the algebra of omega that you get by multiplying omega in all possible ways with itself and other simple operators must generate the entire algebra. That doesn't tell us whether the horizon is smooth or not. So it's whether if we can find these A tilde omega operators, that tells us if the horizon is smooth. So as we will construct in this lecture and next, we will find some A tilde omega operators, and that will be a powerful argument that the horizon is smooth. But until you construct them, you can't say that the horizon is smooth or not.
Okay, yeah, thanks.
Okay, great. So that's what we are trying to do. So we want to understand first. So before we construct these A tilde omega operators, we want to understand these two notions, preliminary notions of the little Hilbert space and of equilibrium states. So let me first explain what the little Hilbert space is. Okay, in fact, before that, I'm going to explain some notion which is even simpler, which is a notion of simple operators. Okay, so it's a simple notion, but it has to do with simple operators. Okay, so what are simple operators, and why are simple operators important? You see, we said that we want to find it's some phi where R is inside, maybe T. We want to find like some operators with the right properties. What does it mean to have the right properties? So we wrote down like some correlators, right? If you transform like phi with you integrate it with some modes, you extract like these A tilde omega operators from phi, then it should have the right correlators with operators outside. And so we have some list of right properties. But in fact, we need to be a little bit more careful. And the reason we need to be a little bit more careful is that what we really want is that we want some operator that has the right properties within simple correlators. What does that mean? So that means that, let's say we take some state, right? This is our state that we are working with today. And we write down, so let's say this is some operator. We write down, this phi. And then we write down another operator. And then we write down psi. Okay? So based on the 2-point correlators that I wrote down, we have some expectations for how this phi should behave when it is inserted in such a correlator. But it is important that, these operators A and B should not be arbitrarily complicated operators. If you consider the entire operator algebra of the theory, if you consider the entire operator algebra, this also contains operators, some B, which have the property that, maybe they take the state and they map it to the vacuum. So this is like some ultra complicated operator, which takes the black hole state and it just maps it to the vacuum. And of course, such an operator exists, right? Because in the Hilbert space, you can always find an operator that maps one state to any other state. And here's an operator that takes the black hole state and maps it to the vacuum. And for such operators, we have no expectations for what, this should give us. So the expectations, these right properties that we derived, these were properties that we derived using effective field theory, right? We said, if you remember the derivations that we did in the beginning of this course, we said, we consider some 2-point function. The 2-point function behaves like a geodesic, and and that's what we use to derive all of these properties. But if you start making like such huge perturbations to the geometry, like something which takes the black hole and just makes it vanish, like turns it into global AdS, then of course, we don't know anything about like 2-point functions. Like, maybe we insert like another operator here, which is outside, but this 2-point function is not a meaningful function if you have also inserted this ultra complicated operator B, which is going to take the state and map it to the vacuum or map it to something totally different. Okay? So for such operators, for very complicated operators, for such complicated operators, we have no expectations. Okay, so we have no expectations for this phi. For these, so these operators, which I'm not writing the T and omega arguments, but there's some operators inside. But when you insert like complicated operators B, or for correlators that involve such complicated operators, we have no idea what this is. Okay, so that's a precise statement. Okay, fine. So now it's important, therefore, that we should restrict our demands to not be absolute demands. And this is actually an important. It's a really important physical point. It's one of the important physical points that came out of this entire discussion. That when we demand that these operators phi of our inside should have some right properties or should click in the right way with correlated with operators outside, we should not demand that these be absolute properties. We should not even demand, for instance, that the commutator, which I wrote previously, which came from some demand from locality or approximate locality, should be an exact statement. But rather, we should say that these are things which should hold within effective field theory, and they should hold for experiments that can be done by the infalling observer. Okay? So simple operators correspond to physical experiments or physically feasible experiments that can be done by the infalling observer. Okay. Of course, the infalling observer is very powerful, so not like us, can do like experiments that test quantum gravity and many other things. So physically feasible doesn't mean humanly feasible. The infalling observer comes from an advanced civilization that knows how to test quantum gravity. But even this infalling observer who comes from this advanced civilization, does not do experiments that will totally destroy the black hole. Okay? So, still does experiments which probe maybe even quantum effects, maybe even gravitational effects, but still does experiments that which are physically feasible. And what that means precisely is that which are well described by effective field theory about the black hole. So there are some experiments, or some questions which are not well described by effective field theory, which are of the kind that I described previously. Effective field theory doesn't help us understand what happens, if you start inserting like operators which have so many insertions that they can make the black hole vanish. There's no sense even in talking about effective field theory about the black hole. So such questions do have an answer, but this answer is only in the boundary theory, which gives you a complete description. From the point of view of the bulk, we don't want any description of what these bulk operators are for such complicated questions. Okay, very good. So now, so let's denote the set of simple operators. So this is the set by asim. Okay, I'll use asim to denote this set of simple operators. Okay, now we want this asim to have some properties. I gave you some physical definition of what this set of simple operators is that, it corresponds to various physically feasible experiments. But in fact, to make our construction mathematically precise, we will also impose some mathematical restrictions on the structure of this asim. Okay? The mathematical restrictions we want to impose is that asim should be a complex vector space. And that is the statement that, if AI and AJ belong to asim, if these are like observables within asim, then, you're also allowed to measure a linear combination of the observables. So it's a simple and physically meaningful condition. You could imagine like observations you could make where you somehow can't measure the sum of the observables. But it's just for mathematical consistency and to make this construction of interior operators make sense, we will demand that the set of simple operators that we have has the property that it's closed under like taking linear combinations of simple operators. Okay. Second, we will also demand that it's closed under conjugation. So if AI belongs to asim, then AI dagger belongs to asim. Okay. Second, it's very important that when we say that we are looking at physically feasible experiments, of course, the set of physically feasible observables that you can find are much smaller than the dimension of all the observables in the theory. Okay? So the second condition is that the dimension of asim should be much smaller than e to the s. E to the s is where s here is the entropy of the black hole, but this is the dimension of all observables. And of course, we don't want to take the set of simple observables to be anything like the set of all observables. And therefore, we take the dimension of the set of simple observables to be much, much smaller than the set of all observables. And the third restriction I'm going to put on this set of simple observables is that the Hamiltonian and other conserved charges do not belong to the set of simple observables. Okay, so in this lecture, I'm just going to consider the Hamiltonian, although what I say also generalizes to other conserved charges, but H does not belong to asim. Okay? This is not because H is not a simple operator. Okay? So this is not because H is not simple, but just because, in the treatment or when we construct these mirror operators, H and other conserved charges are going to require special treatment. So this is just, this is not like this is not a physical restriction. It's just a restriction that we are currently putting on our set. So when I write an operator which is an element of this asim, I'm never going to be referring to the Hamiltonian, which is H. H is the Hamiltonian, or other conserved charges. I might have like other charges in the theory, and I'm not going to be referring to any of those charges either. And that's not because they can't be measured. In fact, as we discussed in this course, it's important in a sense for many things, including for holography to work, that you should be able to measure these charges and the Hamiltonian. But just, we need to be careful about how to treat them. So we will, at the end of this lecture, now hopefully, or maybe at the beginning of next lecture, discuss how to include these operators H. But for now, we don't have them. Okay, so this is just a temporary restriction. Okay, so I've put various conditions on this set of simple operators. So what is, we can be a little bit more precise about what this set of simple operators can be. So there is there are actually various choices you can make of this set of simple operators. So, these conditions that I wrote down are rather general conditions, and you will see that the construction we will describe of these mirror operators works, provided your set of simple operators meets these conditions, and there is no unique choice of asim. But when these mirror operators were first described, which was in archive 1310, a particular choice of this asim was made, and we will stick to this choice of asim. And the choice we will make is as follows. Okay? So let A omega be the modes described previously. And then we consider like simple polynomials in A omega and A omega dagger. Okay. Remember that I'm writing A omega, but in fact, you have all sorts of frequencies available to you. So the statement is that asim is the span of A omega dagger, and other kinds of polynomials. So we might have A omega 1, A omega 2, maybe A omega 1, A omega 2 dagger, A omega 1, A omega 2, A omega 3 dagger, and so on. Right? And so on. So we consider simple polynomials in these modes that we had previously. So this, as we discussed a little bit earlier, if you kept going forever, if you kept multiplying all of these O omega operators, all of these A omega operators, I'm using A omega, which is just the same O omega operators, just normalized so that they are canonically normalized. So if you kept using, if you kept multiplying these operators together, you would end up generating all possible operators in theory. So it's important that we put a cutoff. So when we write simple here, the simple fact corresponds to the fact that we put a cutoff on the order of polynomials. Okay. So that cutoff is not precisely determined. It's not something that's given. You could decide that the cutoff is 100 or it's 1000. But it's very important that the dimension of asim, as I said previously, should be much smaller than e to the s. So if you put any order 1 cutoff, even if it's much larger than 1, if you put the cutoff to be 10,000, remember this s scales like n squared. This entropy scales like n squared in AdS CFT. And so provided you put any order 1 cutoff here, you can go up to a omega. You can consider polynomials with up to 1,000 insertions. That will still ensure that this condition is respected. Okay. So when we will talk about this set of simple operators, we will talk about this set of simple polynomials in A omega and A omega dagger. Okay. It is possible to make other choices. And it might be, that for some physical reasons, other choices are more useful, but we will not explore these other choices, and we will just consider this set of simple polynomials. Okay.
Okay. Me,
yeah.
Can I ask a question?
Yeah, sure. Yeah.
Yeah. So in these conditions you listed for asim, there is no condition about the algebra that is being generated by all the operators in asim.
I was just about to say that. Yeah, go on. Yeah.
No, because I was just wondering that if I'm allowed to multiply these polynomials, then I'm going to exceed the cutoff that you.
Yeah. I was just about to say that. So
okay.
Yeah, exactly. So I think So as was just asked, this asim is in general is not an algebra, as you can see here. What that means is that if AI belongs to asim and AJ belongs to asim, it does not imply that AI AJ belongs to asim. And that's pretty clear from this definition that we have here. We put a cutoff on the order of polynomials. And so it's clear that, if my cutoff was 10 and I took like 2 polynomials of order 9, both of which are in this set of simple observables, and then I multiply them together, I'll get a polynomial of order 18, and that is larger than 10. And so that has exited my set of simple operators. And this is something that is almost unavoidable when you consider a notion of simple operators. At least I don't know how to get around it. So whenever you coarse grain the set of observables so that you're considering like a set of simple operators, as we are doing here, you can demand that a set of observables, forms a vector space. You can demand that it's closed under conjugation, but it's very hard to demand that it forms an algebra. And that is because, if you have a coarse grained set of observables and you start multiplying them together and you allow arbitrary products, you often end up generating, the entire algebra of the theory. And so you exit the coarse grained space. And so there's a physical reason for this. The physical reason is that, because we are considering experiments that are, that can be done by the infalling observer, and because we are putting this physically feasible restriction, we may not sometimes be able to measure like, OI or AI AJ. If we can measure AI and if we can measure AJ, we may still not be able to measure the product AI AJ. Okay. So that is pretty clear from the description we had previously, where we considered polynomials which had a cutoff on their order. And in those, when you consider polynomials which have a cutoff in this order, they do not form an algebra. Okay. But you see, for many purposes, in many cases, AI AJ may belong to ASIM. So it's important that it's not exactly an algebra in that, because AI belongs to ASIM and AJ belongs to ASIM does not mean that AI AJ belongs to ASIM. But in many cases, it is the case that if AI and AJ belong to ASIM, then the product AI AJ also belongs to ASIM. So in the analysis that we'll do below, we will in fact not be so careful about the fact that AI AJ doesn't belong to ASIM. And often we might write down like simple operators, and we'll assume that, if you take these simple operators, then the product of these simple operators also belongs to a set of simple operators. But of course, one needs to be careful if one does this analysis very carefully about the fact that sometimes this product may not belong to the set of simple operators. And conceptually, it is very important that this is not an algebra, because that's what allows you to make a meaningful restriction to a set of simple operators. So in the algebra that we'll do now, or in the analysis that we'll do now, we will sometimes forget about this subtlety, but remember, it should always be there at the back of your head. And if you find like a problem or a paradox, you should go back and remind yourself that sometimes, it might be the case that you have two elements of this algebra of this set of simple operators, but the product is not a simple operator. Okay, I hope that answers the question. I was about to say that, but I hope that answers the question.
Yeah, thanks.
I have a question about this.
Yeah.
So we just write down these three conditions or four, I guess, for ASIM. But how are these conditions related to the statement that we made earlier that simple operators are operators that advanced infalling observer have?
So they just these three conditions are not, as I said. So if we look at this, so if there's no way to. This thing about what are the set of observables that the infalling observer has access to is a physical statement. So here is a set. Here is ASIM. Okay, if you want to think like more concretely and not about like abstract simple operators, just think about this thing which I've underlined. So we can just think about this set of simple operators, which is a set of like simple operators in the modes of the fields. The point is that sometimes it might be useful to think not in terms of the modes of the fields, but in terms of fields in position space. Sometimes it might be useful to think of projection operators. Sometimes it might be useful to think of bounded operators. So none of these operators are bounded operators. So, you might say that I find it convenient to think of bounded operators. And maybe one of those is actually the right or the more physical thing to do. And that's why I didn't want to, start by saying that this is the set of simple operators and just go on with that. And so I was trying to write down some more general conditions that a set of simple operators has to satisfy. Of course, in addition to those three conditions, there's a more ill-defined condition, which is it must correspond to physically feasible experiments, which is hard to make precise mathematically. But if you're right, and that's kind of ill-defined. And so if you'd like a very concrete example of what ASIM is, then here is an example. I just wanted to emphasize that it is possible to make other choices. And some examples of other choices are consider operators in position space rather than momentum space, as I said, or consider projectors or consider bounded operators. And maybe there are other possible choices as well. That's why I said whatever choice you make, you should make sure that those three conditions are met at least. Otherwise, the whole construction will not make sense.
So I have a question.
Yeah.
Do we put a bound on omega as well?
Yeah, good. So you should put a bound on omega as well. Thank you. So we should put a bound. We should put a bound on omega as well, and that's important, so that thank you, so that you're not considering excitations which are extremely high energy. So if you start considering like excitations which have energy of order n squared, so omega is like an order 1 frequency here. If you start considering excitations which are of order n squared, then once again you will come back to operators of the kind we had previously, where you might be able to annihilate the black hole. And indeed, so you should put a bound on omega, and you should make sure that it's order 1. As I said, this is, so if you want to look at this very precisely, some of these cutoffs were discussed a little bit more precisely. We also need to discretize, omega a little bit. So I've written like a omega here, but I haven't been careful about how it was discretized. So we need to discretize these a omegas a little bit, and that was discussed a little bit. It's discussed a little bit in this paper where we first discussed these issues. Yeah, you're right. So one of the cutoffs we need to put indeed is that the omega, the frequency should not be too high.
Thanks.
Yeah, so I just want to verify one thing. Yeah. So you gave an example of ASIM, and it's just an example. Yes. And there is nothing which stops us by putting a tildes into that also.
A tildes, no, you shouldn't put a tildes. A tildes are not yet defined, so you can't put a tildes into ASIM yet. ASIM is something which you have to define before you define the a tildes. So you shouldn't put a tildes into ASIM. That would not make sense. We are still trying to define the a tilde, so you shouldn't put a tilde into a set of simple operators ahead of time. Okay. So in this set, this is a preliminary step to defining the set of simple operators.
Okay, yeah.
Okay, great. Okay, great. So very good. So let me just point out something, which is that because of these conditions and these cutoffs that we've put, also on the frequency, it's important that if AI belongs to this ASIM, then in general, AI psi is not equal to 0. Okay, so AI psi, and that's this, that's some no annihilation property. For those of you who are familiar with the algebraic discussion of these issues, this is the statement that psi is separating with respect to this set of simple operators, in that there is no element of this set of simple operators that can annihilate psi. But in any case, this is a very physical statement. It's the statement that we made previously, that if ASIM is some set of simple operators, certainly for the set of simple polynomials that I described previously, you can't act on them and make the black hole vanish. Okay? So you can't just destroy the black hole by doing that. And therefore, you expect that for the set of simple operators, you can never annihilate the state psi. Okay? So this will be important for us mathematically. It might be, by the way, that for some states psi, it does happen that maybe acting with one of these simple operators AI does annihilate the state, right? You can always imagine, even you have a high dimensional space and you have some very complicated set of microstates, you might always be able to find some linear combination of the operators AI so that AI psi is equal to 0. And if that happens, then this mirror operator construction that I'm going to describe will not be able to go through. And that is a sign, in fact, that the state psi is pathological. Okay? If psi does not satisfy this property, so you can think of this as a condition on the state psi rather than a condition on the set of simple operators. So you define the set of simple operators as I described previously. And then, you do expect that in general, for a generic state, AI psi will not be 0. But if psi does not satisfy this property, then it is pathological. And, such states may have, so you would expect that such states, or this is actually an indication that such states might have a firewall. But such states are obviously rare, and the reason they're rare is just by dimension counting. Just by dimension counting, you have some set of simple operators which has dimension much smaller than the Hilbert space from which you're allowed to pick microstates. And therefore, you expect that you act with one of these simple operators on the state, and you're not able to annihilate the state. So most states are not of this kind. And so most states do satisfy this simple property. But some states might not satisfy this property. And if they don't, then they're pathological states. And you don't expect to be able to find a smooth interior for such states. Okay, good. So we spent a lot of time on all of these issues, but now we can actually discuss the little Hilbert space. So little Hilbert space is actually quite simple once we've said all of this. So I'll denote the little Hilbert space by H psi, and it simply is the space obtained by acting with A sim on psi. Okay. So more precisely, it is the span of AI psi, where AI belongs to A sim. So there's a physical way of saying this. We said that this A sim corresponds to some set of simple experiments that can be done by the infalling observer. The little Hilbert space corresponds to a set of states that the infalling observer can reach by doing such simple experiments. Okay. So, if the infalling observer acts with one of these operators A1 on psi, then you move out of the original states. Of course, the infalling observer has the ability to do some experiments, and these experiments are all described within an effective Hilbert space, which is this space H psi. Okay. So this is all we mean by the little Hilbert space. Here is one way to picture the little Hilbert space. If you have some big Hilbert space, say there's a big Hilbert space, then one way we picture the little Hilbert space is this way. Okay, so here's the state psi. So this is the full Hilbert space. And within that full Hilbert space, we have this little Hilbert space, which is centered around psi, which has this property. Okay. And the reason it's much smaller, I mean, this cartoon is only two-dimensional, but these Hilbert spaces are all both high-dimensional. But remember, the dimension of this little Hilbert space is much smaller than the dimension than e to the s. And that is because the dimension of the little Hilbert space is equal to the dimension of A sim. It's equal to the dimension of A sim because by the condition that no element of A sim annihilates the state psi, every element of A sim or every element of a basis of A sim acting on psi generates a linearly independent state. And therefore, the dimension of H psi is the same as this dimension of these simple operators, which is much smaller than e to the s, as we already described. And that's why you should think of H psi as being a small space embedded inside this big Hilbert space. Okay. Okay, great. This space, by the way, is something that's also called the code subspace. So it's also called the code subspace. But in fact, historically, the context in which this code subspace was first introduced was in the context of black holes. So this is where the code subspace was first discussed. And so we'll continue calling it the little Hilbert space. But for those of you who are familiar with the terminology of the code subspace, which is used in discussions of quantum error correction, that's exactly the same notion as this notion of the little Hilbert space, which is simply that you have some microstate psi, and about this microstate psi, you think of all possible simple operations, and that generates for you a small set of the full Hilbert space, and that's the set that we're interested in. So this code subspace was first introduced. Was first introduced as the little Hilbert space about the vacuum. But of course, you can think of it more generally about any other microstate as we are doing. And so this is, there are two different terms that are sometimes used in the literature, but they mean the same thing. Okay? And physically, they just mean they both come from precisely the same physical motivation, which is you want to consider the set of simple experiments that one can do if you're in a given microstate, and you don't want to consider complicated experiments. Okay, great. So that is what I wanted to say about the little Hilbert space. Before I describe the construction of the mirror operators, I need to do a little bit more preliminary work. And it also describes the notion of equilibrium states. So what is an equilibrium state? So physically, and it'll become clear perhaps in tomorrow's lecture why this notion of equilibrium states was important. So physically, an equilibrium state is one where we have a black hole that has settled down. So, we say that we have some black hole. This is the diagram that we were drawing in the beginning of this discussion of large black holes. We have some black hole. The black hole was formed by some infalling matter. There's a horizon. There's some infalling matter. And we want to consider the physics somewhere here. So we are interested in the late time physics, right? And therefore, if you're interested in the late time physics, you're not interested in the details of the infalling matter or whatever else initially formed the black hole. And you do expect that the classical geometry, at least at late times, has settled down to something that is smooth. And that is the kind of state that we're interested in. We will later also consider what happens if you take such a state and you hit it, or you additionally excite the geometry in addition to whatever infalling matter made up the black hole. But for now, we will describe this construction of mirror operators in states which are in equilibrium, which physically means this, that whatever formed the black hole was far in the past, and we are interested in the late time physics. But there's a mathematical way to actually check whether something is in equilibrium state or not. And the mathematical way to check whether something is in equilibrium state or not is to check the time dependence of observables. Okay? So let's say we have an observable, we have this observable AP. We can now ask what happens if you evolve this observable in time. So we can consider chi p of t, which is the expectation value, but it's an expectation, it's a time evolved expectation value. Now, what do we expect for the expectation value of such an observable if the picture we have in mind is this picture? So the answer is that for such an expectation value, we expect that this expectation value does not depend on time. It might depend on relative times of operators within AP. If AP itself is a product of operators which are at 5, 0, and maybe an operator 10 seconds later, then that relative time is important. But if you time translate all of AP, then there should be no time dependence in the expectation value at all if you're at late times. In fact, you can ask how much the time dependence has to be, and using the kinds of estimates that we made last time, you can actually estimate that for a generic state in equilibrium, you expect that this is of order e to the minus s by 2. Okay. So for a state which satisfies this, we will say that the state is in equilibrium. Okay. So this is the condition, our condition for a state to be called an equilibrium state. And it is the condition that the correlators or expectation values or experiments that the infalling observer does in the state are effectively time independent. They're not exactly time independent because you always expect small fluctuations, and it may happen. And of course, if you take this time to be very large, it's important when we say this again, that if you take this time to be very large, then, of course, this breaks down. If you go to long enough times, then you start seeing funny effects, you start seeing Poincare recurrence and so on. So here we are talking about time scales that might be long, but that are much smaller than time scales which involve or which lead to Poincare recurrence. And the condition for a state to be called an equilibrium state is just that the observables in the state are time translationally invariant. And this is a condition that we expect to hold on physical grounds for the late time physics. And it is going to be one important constraint that we're going to put in the states that we're considering. And we will consider later how to generalize away from such states. Okay. By the way, as you will notice, this is one condition on an equilibrium state. You might need other conditions for this late time, for a state to be in equilibrium. So we've put one condition, which is that, the state is observables are time translationally invariant, but that might not be the only condition you might need to put. When we physically, what we're interested in is the late time physics of some black hole which was formed a long time back. And the way we formulated that is by this time translational requirement, or this time invariance requirement. But maybe there is something else that is required to specify this notion of an equilibrium state. And that's an interesting question to which, as far as I know, the answer is not known. But for the purposes of this lecture, we'll just take this to be the definition of an equilibrium state. Okay, great. So now we've done all the preparatory work, and we're in a position to define these mirror operators. If there are any questions at this point about the notion of equilibrium states, I can take them, or about the little Hilbert space, which came to your mind now. And then we'll go ahead and describe the construction of the mirror operators. Okay, great.
Just one question, sir.
Yeah.
So you had this condition that AI psi should not be 0.
Right.
So would it? Yeah, I understand that you should have operators in asim such that AI psi is not equal to 0. So let's say you had some order 1 operators for which this is true, that AI psi equal to 0. Would everything still work? I mean,
no. If you had operators for which AI psi was equal to 0, like these operators,
if you had a single operator for which it's true, even then it would not work.
The construction would not work. Yeah, we will see the construction will not work. Indeed.
Okay. Thanks.
And you wrote down this little Hilbert space about vacuum. So where does this vacuum
No.
lie in this big?
The code subspace is a little Hilbert space. When the code subspace was first used in this, when the code subspace was first introduced as part of this error correction story of Dong, Almeri, and Harlow, they used the term code subspace as the little Hilbert space about the vacuum. So I was just trying to explain that the code subspace was first used in this context. For us, the vacuum is not there at all. We just have this little Hilbert space about some state psi. I'm just saying that, for us, psi is a black hole microstate. You could start considering the same kinds of little Hilbert spaces about the vacuum. And, when one discusses the code subspace in AdS CFT about the vacuum, that's the little Hilbert space about the vacuum. But here we are discussing the code subspace about a black hole microstate. So there's no vacuum here in our discussion. We are always in a black hole microstate, and we are looking at the code subspace or the little Hilbert space about the black hole microstate.
Yeah. Okay. Yeah.
Thank you. Okay, great. Okay, great. So now let's define this these mirror operators. So, and the definition is as follows. Okay, so let's pick a basis for this little Hilbert space. Okay. In the end, the definition will not depend on the basis, but just to make it explicit, I'm going to pick a basis for the little Hilbert space, and I'll denote the elements of this basis as AM, as some VM. So these are my elements of the basis, where this AM belongs to asim. And this M can run from 1 to D. And by D, I just mean the dimension of asim. So when I write, just to avoid writing dimension of asim, I'll just use D for the rest of the lecture. And here is a basis of states for the little Hilbert space. And this is a basis because of the condition that we had that, none of the states, none of the operators from this set of simple operators annihilates the state. And therefore, I can define this VM. Very good. Okay, then I'm going to define my mirror operator to have the property that A omega tilde on VM is equal to UM, where UM is this same operator AM, but with some additional insertions placed to the left of this operator. So UM is a different vector, which is also in the little Hilbert space, and it is this vector. So it's this operator AM, and then I have e to the minus beta omega by 2, and an A omega dagger acting on psi. This is the mirror operator A omega tilde. So it's a specific mirror operator. It's the mirror operator of A omega, and that mirror operator I define in this way. Okay? And then this is the definition of how the mirror operators act on a basis of the little Hilbert space, and it should be extended to all of its psi by linearity. So that means that if you have a linear combination of these VMs, then for a linear combination of the VMs, these A omega tildes just act linearly, and that is therefore the definition of the mirror operators. Okay? This notion of linearity can be made a little bit more precise. You can define a metric on this basis, which has the property that is equal to delta of MP. And with this metric, this A omega tilde is just given by where these vectors were what I wrote previously. Okay, so Vn is An on psi, and Um is Am e to the minus beta omega by 2 into A omega dagger on psi. Okay. So this is a definition of what these mirror operators are. So I'm telling you how these mirror operators act in the little Hilbert space. And the way I'm defining these operators is I'm defining these operators to be the operators that cause the transition from one state, from this state to this state with this metric. Okay. So this is my definition of the mirror operators. This is the mirror of this operator A omega. I can also define a mirror operator for A omega dagger, and that is defined with a different, notice the factor of e to the beta omega by 2 is different. And here you have now on the right hand side at A omega. So when you look at the mirror of A omega dagger, you get in the right hand side A omega, and then you have a factor of e to the beta omega by 2 times Am acting on psi. So let me emphasize that, as I said in the beginning, it is not the case that A omega dagger is e to the beta omega by 2 into A omega, but it is the case that its action on some vector in the little Hilbert space can be written in this way. Okay, and of course you could write down similarly using a metric an expression of this kind, which I won't write, but it's a trivial expression. You would just have to replace these UMs with these kinds of vectors instead. So let me, this rule that I've given you for describing the mirror operators A omega and A omega and the mirror of A omega dagger, in fact, is sufficient to construct the mirror of any operator. So for instance, let us say I wanted to construct the mirror of A omega tilde and A omega dagger. Okay. So this is the mirror of the number operator or the number operator plus 1. And how do I determine what this mirror is? Let's say I wanted to determine what was the action of this operator on the state side. So this recursive procedure that I'm going to describe now is nice, and it's something that's useful to know, because this is crucial in how these mirror operators work. So first I act with this operator on psi. I have a rule for how this operator acts on psi. In this case, Am is just 1. So this operator, let me leave the operator that I have on the left unchanged. And then I have e to the minus beta omega, sorry, not e to, this e to the beta omega by 2 into A omega acting on psi. This, I just used the rule I wrote down last time for how the mirror of A omega tilde acts on psi. And now I have A omega tilde acting on this. But this I also know because this is now a simple operator. So it's one of my Am operators. So I know how A omega tilde acts on this state, not on psi, but on this state. And the way it acts on this state is it goes to the right, and I get an e to the beta omega by 2 A omega. Here I just copied this. And then I get an e to the minus beta omega by 2 into A omega dagger on psi. And so the factors cancel out, and I just get A omega dagger on psi. Notice that this would not have worked if A omega tilde dagger had just been A omega, or if it had been e to the minus beta omega by 2 into a omega. If that had been the case, you would have gotten a omega in front. Okay, but notice that this, the way we've defined the operators, we've defined them cleverly so that if you consider an expression which is the number operator of these mirror operators, this number operator automatically becomes the number operator of the ordinary operators. And even though a omega dagger was defined with an a omega, by means of this process, you see that the mirror operators interchange. So in the first case, you replace this with an a omega, but in the second step, this a omega moves to the left. So the final answer you get is just this. Okay. So this is just some simple algebra. I mean, I might have said too many words to describe some simple algebra, but this is how one can generate the mirror of any polynomial of these a omega tildes and a omega daggers. There is, of course, a general rule. You can just, you can bypass this process of doing it step by step. Yeah, just one second. And the general rule is that if you want to define the mirror operator of some polynomial or of any simple operator, then the definition is that the action of this mirror operator on any element of the little Hilbert space is defined by this rule. So this is the general rule, and you can check that everything we wrote previously falls into this general rule. Never mind. Okay, so this is the general rule, and this general rule encompasses the rules we gave previously, including also the rule for this polynomial. So I gave it step by step, but if you want to bypass something, then this is the general rule for constructing the mirror of any simple operator. It is defined, its action on the little Hilbert space is defined by this rule, and by this condition we had from the fact that a omega psi, am psi is never 0. This is a set of linear equations that you can solve for a and tilde, and this set of linear equations has a solution, and that solution is the definition of this mirror operator, a and tilde. Okay. Yeah, sorry, there was a question.
So above, I think you gave the action of a omega tilde on the state V.
Yes.
But applying it to psi, how do you find the action of a omega tilde on psi?
Psi is just psi is just 1 times psi, right? So Vm was like any element of
okay, sorry.
Sure. Am equal to 1, then you get psi itself. Yeah, so I should have said 1 is a simple operator. Yeah, but yeah, you just take am equal to 1.
Okay, thank you.
Okay, great. Very good. So now, the question.
Yeah. So, actually, maybe slightly unrelated, but are these? Is this definition related to this Tomita Takisaki operators, or this is?
Yes, it is. Although I wasn't planning to discuss that in this course. So indeed, there is another way you can define these operators using Tomita Takisaki theory. I was thinking of putting some of that in the assignment. But yes, so the short answer is yes, but it'll take us too far astray to go into that description. But indeed, these operators are related to the operators that appear in this Tomita Takisaki theory. So there's another way to write these operators, which is some elegant formalism, which is rather than writing this, you replace this with some modular operator, and you put in some these antilinear S operators. But we might have an assignment question on that, but I don't want to go into that. It'll take us too far astray.
Okay, cool, thanks.
Okay, so we define some mirror operators. So this is the straightforward down-to-earth way of defining it, the definition I gave, and there's a mathematically more sophisticated way of doing it, which just involves a little bit more background, and so takes a little bit more time, which is what you said. So let's just check that we wrote down some definition, but why does this definition make sense? Why does this satisfy the rules that we said it does? So let's check that it does. So the first thing, of course, we need to check is 2-point functions. So what about you remember when we said that we had these operators a omega tilde, they had to have the right 2-point functions. So the first thing we can check is just what about the occupancy of the mirror modes? This occupancy, in fact, is like the occupancy of the partners of the Hawking radiation. So remember, these A omega tilde modes are the partners of the modes that come out as Hawking radiation. And so we expect that these A omega tilde modes will also be thermally occupied. In fact, we just did a calculation of A omega tilde, A omega dagger acting on psi. And this is therefore just, this is by the calculation that we just did. But we know what this is. This is now a simple operator. This we don't need, this we know from other calculations that we've done. And we know that this is a black hole, which is in equilibrium, and that we know from a calculation outside that this is given by 1 by 1 minus e to the minus beta omega. So that tells us that the mirror operators do have the correct occupancy that we wanted them to have. Of course, there's another correlator, which is the entanglement of the operators inside and the operators outside, which is this 2-point function. Now, when you have this 2-point function, you should just use the rule we had. And remember, the rule is that you put this A omega tilde to the right, and you put a factor of e to the minus beta omega by 2, and you turn it into an A omega dagger. Now we have the same thing that we had above. So this answer for this expectation value is just this, but there's an extra factor of e to the minus beta omega by 2. And we just get e to the minus beta omega by 2 by 1 minus e to the minus beta omega, which is indeed what you expect for the correlation function of outside and inside. You do expect precisely this factor. You can also check other things. You can check, for instance, what happens if you consider A omega tilde dagger with A omega dagger. This should have, in fact, the same correlator that we had previously. And you can see that this also works out because this is given by A omega dagger. And now you move an A omega here, and you get an e to the plus beta omega by 2. And that is good because this operators here, this expectation value is e to the minus beta omega by 1 minus e to the minus beta omega. That is this expectation value. And so when you multiply this with an e to the plus beta omega by 2, you get once again what we had previously, which is this. So you see that this 2-point function also works. Okay? So you see that at least the 2-point functions that we desired do work. So these mirror operators do have the correct 2-point functions with themselves and with these simple creation and annihilation operators. Okay, now I want to say something which is important, which is about the commutators. So remember, we also want that A omega tilde into A omega is equal to 0. Let me, at least within simple correlators. Now, as was asked in the beginning of this lecture, there is actually no operator which really exactly commutes with both A omega tilde and A omega dagger. There is no operator which exactly commutes with A omega and A omega dagger, because in a quantum field theory, so in the bulk, actually even from the boundary point of view, A omega dagger, and by this I don't mean for a single frequency, but for all possible frequencies. So they generate the entire algebra. So historically, at least in the AMPSS paper, this was an important argument to suggest that you cannot have these operators A omega tilde because look, such an operator just doesn't exist. Okay. So in fact, one of the common analogies that was used often was these qubit models. And if you think of these qubit models, then the analog of these A omegas and A omega daggers are like the spin operators at a site. And of course, there is no operator in the theory that commutes with all the spin operators, at a site. So if you were to demand that A omega tilde and commutes with A omega and with A omega dagger exactly, then of course such a thing doesn't exist. And so the key point is what got erased when I copied from the previous slide, is that you want this commutator to be 0 only within simple correlators. And in fact, there is no operator that commutes exactly with A omega and A omega dagger. There is something that commutes within simple correlators, which we sometimes denote by putting a dot equal to. This dot equal to basically means this. It means that, this is an equation that holds within simple correlators. Okay? So let's check that this commutator works out correctly within simple correlators. And the simple way to check that, in fact, we don't even have to do it only with A omega or with A omega dagger. Let AN be any simple operator and consider A omega tilde on AN psi. By the rules I just described, this is e to the minus beta omega by 2 into AN into A omega dagger on psi. And of course, this is the same as AN on A omega tilde on psi. Right? Because if you just take A omega tilde and act it on psi, you get precisely this A omega dagger with a factor of e to the minus omega by 2. And so you see that A omega tilde on AN on psi is the same as AN A omega tilde on psi. That tells you that A omega tilde and AN on psi is equal to 0. But I emphasize it does not imply that A omega tilde and AN is equal to 0. It just means that the commutator annihilates psi. So notice the difference between this statement and this statement. This is an exact operator statement, which we know cannot be satisfied. There are no operators that commute exactly with A omega and A omega dagger. We know such an operator doesn't exist. So there is always some non-zero commutator, because AN is made up of A omega and A omega dagger. There is whatever these mirror operators are, if they belong to the algebra of the theory, they must have some non-zero commutator. But it could be that they have a 0 commutator when you act on the state psi. And this implies that if you consider some correlation function of this kind and you insert something else, this correlation function is 0. Not because the commutator is 0, but because the commutator is cleverly designed that it is not visible within simple experiments. Okay. So the commutator is non-zero, but invisible within simple experiments. So this is an important point about how these mirror operators not only have the right 2-point functions, they also have the right commutator. And it's very important that this commutator, is right in the sense that, you don't demand that the operator behind the horizon exactly commutes with the operator outside the horizon, which in any case, you should not demand, because, we've discussed many times how there are these subtle loss of locality in gravity, but you can demand that it commutes to good approximation with the operator outside the horizon. And that is, what goes into the definition of these mirror operators, which is that you design them so that the commutator is non-zero, which you're forced to have, but it's invisible in simple experiments. So there was one of the arguments stating that these A omega tilde should not exist was this, that you can never find an operator which has 0 commutator. But here we see that you can find an operator, which has non-zero commutator, but which cannot be detected. Okay.
Can I ask one question?
Is there a question? Yeah.
So in fact, one can generalize this to a general mirror operator capital A tilde, right? Because from your earlier formula, which you had for a general operator, I guess this capital A tilde will also commute with.
Correct. Absolutely. That's right. Thank you. So indeed, it is the case that all the mirror operators, where I have not written equal to, but dot equal to, which is the statement that, it commutes within simple operators. Okay, great. So I have, but okay. So I just want to say something, and then in fact I'll stop because I think I won't be able to finish this part here. Let me just say one thing. Remember, there's a subtlety, okay? And we'll discuss the subtlety tomorrow. The subtlety is that we know that A omega tilde shouldn't commute with everything. Okay? So in particular, we know that there is this commutator with the Hamiltonian, which is the wrong sign commutator. So remember, we discussed last week this commutator, which comes from the fact that these operators behind the horizon have to be gauge fixed or have to be dressed to the boundary. And when they're dressed to the boundary, if you perform a large diffeomorphism, which is what is generated by H, you move the operators not only outside the horizon, but also the operators inside the horizon. And that tells you that the commutator of the Hamiltonian with the A omega tilde is not 0. So it should not be the case that, if you insert the Hamiltonian, you should get 0. And in fact, this is the reason we excluded H. This is the reason we excluded H from ASIM, because we didn't want the mirror operators to commute with the Hamiltonian. I've written conserved charges and I'm talking about H, and that's because there's an analogous story for all conserved charges, even for non-abelian charges, which is discussed in some detail in the reference I described. But this is the reason we didn't include H, because we did not want to ensure, we did not want that H with A omega tilde be 0. Rather, H with A omega tilde has to have some specific value. And for those of you who remember last week when we discussed these paradoxes, it was this wrong sign commutator, the fact that you got plus omega rather than minus omega, which went into one of the paradoxes that suggested that this A omega tilde does not exist. So I think I'm almost out of time here. So I won't describe today how you can construct this, how you can generalize this construction to include H, but we will see tomorrow. So we will include H. H in our set of simple operators. Okay. So let me actually stop here because this will require a few minutes, but I am already running short of time. So I'll describe tomorrow how you also can get this commutator correct. So it's not just that you want all commutators to be 0. You want almost all commutators to be 0, but not the commutators with conserved charges. And this we will see tomorrow. So let me stop here. And if there are more questions, I can take them now. And maybe all the questions were already asked.
One thing that H in this Hamiltonian, this will have like all the dependence on all values of omega. Na? This so it can be some simple observable.
No, but so Hamilton is not a complicated observable. When I excluded from ASIM, it was just a mathematical exclusion. I just said, in the beginning, I said we don't include H as part of ASIM. So you could have thought, why? Where we? So I said this is a temporary restriction, which I wanted to lift by the end of the lecture, but now we'll lift tomorrow. So this is not because H is not simple. It is just because it requires special treatment. And the reason it requires special treatment is the reason we have at the end. It's the fact that, we want A omega tilde, the mirror operators, to commute with simple operators, but not commute with all simple operators. They shouldn't commute with H. And this is important. Sometimes, there are constructions in the literature which try and generalize these mirror operators and set the commutator with H to be 0, but those don't work. Okay. So it's important that, there's a non-zero commutator with H, and that comes on physical grounds. It's because, the operators in the interior, these phi operators in the interior have, when you specify local operators, you need to dress them to the boundary. And when you dress them to the boundary, you specify their behavior under large diffeomorphisms. and that's what gives you this non-zero commutator. And so we shouldn't have had a omega tilde with h equal to 0, and that's why we excluded h from asim. It wasn't because h is not simple, it was just that it needs special treatment. And this, you see here that it needs special treatment because the commutator of a omega tilde with other operators is 0, but not with an. Sorry, does that not answer the question?
Yeah, my question is like H is the full quantum gravity Hamiltonian. So like, how can we just write it with some simple set of operators?
How can you write it as some simple set of operators? Sorry, H is, yes, H is the Hamiltonian, but H is also, as we discussed last time, can be, as we've discussed many times in this course, can be measured by just looking at the metric at infinity. So H is also a component of the metric. So it's some integrated metric component at infinity. And so H is something which we believe that it's something that can be measured, right? You can measure the energy of the black hole, and you can measure the energy after an experiment as well. And so H is physically unobservable. And previously, when we discussed this notion of holography, we included many times. I mean, we discussed many times how H is a component of the metric. And so H is physically a simple operator, but it's a slightly special simple operator. And so we are treating it separately. I don't know if that answers the question.
Yes, it does. Yeah. Thanks.
Yeah, I have a question about this mirror operator construction.
Sure.
So we construct these mirror operators in equilibrium states, right? I mean, we define equilibrium states by time translation symmetry.
Right.
So can we similarly construct these operators for at least near equilibrium states?
Yes. So yeah, we can, and that we'll describe next time. So indeed, this is also a restriction we've put right now, and we will describe next time how you can construct it, how you can do this construction in more general states. So I'll discuss that tomorrow as well. So we'll discuss this commutator, and then we'll immediately discuss after that this issue of how you could construct these operators in more general states.
Okay, thanks. Okay.
Maybe a trivial question. Is the maybe I can answer this question by myself, but let me ask: is the mirror of a mirror operator the operator itself?
Yeah. So the way we defined it, it is a right. So the way we defined it, there's no sense of a mirror because we only defined a mirror of simple operators. We define this mirror by these rules, which is that we define the mirror here. So by this kind of definition of a mirror, there's no sense of a mirror because we define mirror of simple operators. But if you use this Tomita-Takesaki kind of definition, where you define the mirror, in terms of this antilinear map S, then indeed it would be the case that the mirror of a mirror would be a mirror, would be the original operator. But in the sense, we are using this very simple-minded approach where for every simple operator, we define a mirror operator. And there's no natural way to, go back to the set of simple operators. To do that, we would have to define a set of EM tilde and then define the AMs to be the set of operators that satisfy the equations on the set of dual simple operators. So in the simple-minded formalism that we are using, there's no sense of a mirror, but if you use a more sophisticated formalism, then you can define a mirror of a mirror, and it is indeed the original operator then.
Thanks. Thank you.
Suvrat, if I may ask a question. I mean, in all of this construction, we are dealing with operators which are mostly for bosonic degrees of freedom, right?
Right.
I mean, is there a trivial extension to fermions? Like, can you just replace all commutators with anti-commutators, or it does not require?
Yeah, so you have to be a little bit careful when you discuss fermions, and right. In fact, I don't, as far as I know, it's not been done in some nice way in the literature. So you would need to be careful when you discuss fermions, and it's actually, yeah, it's in some sense probably quite simple, but it's also true that it's not been done carefully in the literature. What you need to do when you have fermions. The fermionic operators are not by themselves observables, right? You need to construct some bilinears out of those fermions. So one attitude you could take is that we'll only consider like bilinears of the fermions because you only want to consider observables. But you're right that that may not, you could probably say something more. And you're right that no one ever discusses that in detail, but it's something that should be doable with some simple extensions, probably. Yeah.
Okay, cool. Thanks.
And one more last question, I guess. So this construction is work on only for the one-sided black hole or for the eternal black hole also?
Good. So for the eternal black hole, we need to be a little bit more careful. So we will describe a construction also for the eternal black hole tomorrow, and we will need to be a little bit more careful about this construction when we do it for the eternal black hole. As it stands, so if you consider operators which are dressed to the right boundary, then this construction is also valid for the eternal black hole. But we will also explain how you need to be a little bit more careful about, for instance, the notion of an equilibrium state. And you also need to be a little bit more careful about the notion of what you mean by simple operators, because now you have operators on the right and you have operators on the left. And so you need to be a little bit more careful about how you generalize those notions. But if you're just going to talk about the eternal black hole and you're going to talk about experiments that can only be done by right in following observer, and you assume that there's nothing that comes in from the left, then indeed this construction would work also for the eternal black hole. If you were considering operators that were gauge fixed to the right boundary and where you're only perturbing the eternal black hole from the right. So it would also work for that. There's another way you can write down, and we'll actually also discuss tomorrow how you can generalize this construction to the set of these time shifted eternal black hole states that we discussed, that we got a paradox for last time. So when we discuss the resolution to these paradoxes, we'll also discuss how this mirror operator construction, as it is defined using these equations, can also be written in a different way, where these mirror operators then become the operators that come from the left theory, but with some projection operators added on, which I'll describe tomorrow. That's not a very clear. That's not a very clear answer. The clear answer is that yes, if you consider the eternal black hole and you only consider simple operators coming from the right and only perturbations that come from the right, then indeed this construction is valid also for the eternal black hole. And we'll also have a little bit more to say about it tomorrow.